Hey guys, Miss Marusik here, and in this video we're going to look at compound stoichiometry problems where we are converting with mass ratios. Now in a previous video we looked at the idea of if we're trying to get between a compound and an element inside of it, we could set up a particle ratio where we say one of the overall particle has however many atoms inside of it. Well, we can do something very similar with a mass ratio. So here what we're going to be trying to do is getting from the mass of the compound to the mass of an element inside of it. And to set up that ratio, we're going to be doing something very similar to what we did in our percent composition calculations, where we figured out, hey, what's the total mass of this entire compound and what a percent of that mass was contributed by that particular element. So to kind of get an idea of how we can use this as a conversion factor, I want to go back and again look at our heart chart that we added to earlier. So again, we have our moles to mass using molar mass, moles to particles using Avogadro's number, and we said if we're trying to get between molecules and formula units and atoms within one of those compounds, we could set up a particle ratio. Well, this time we're going to be adding to the other side of this chart. So let's talk about this mass side here. So what we can do on this portion is we can say, hey, if we have the mass of specifically some sort of compound, I can get back and forth between that mass of the compound and the mass of an element within. And we're going to do that by setting up a mass ratio. Now again, let's talk about some examples of what a mass ratio would actually look like. So again, I'm going to use something that we're kind of familiar with. I'm going to use as an example again, water. Water has a total molar mass of 18.02 grams. So think about what we would do, say, on a percent composition problem. We would put that total molar mass of 18.02 grams of the water on bottom, and let's say we were trying to get 2 grams of hydrogen inside of it. Well, out of that 18.02 grams, think about how many grams came specifically from hydrogen. Well, there's 2 hydrogens inside of there. So instead of just putting 1.01 up here, we're going to put 2 times that 1.01 up here. Or you could just go ahead and write 2.02. And that would be the grams of the hydrogen inside. Or you could flip-flop that ratio around, depending on where you needed your units. So you could say, hey, 18.02 grams of water on top, and out of that, 2.02 grams were hydrogen inside of it. Obviously, you could do the same exact thing for oxygen. It's just there you would have 16 grams that came from the oxygen versus the 18.02 grams of the total water. So you notice these look very similar to what we were doing with percent composition, where we did the part molar mass over the whole molar mass times 100. It's just here, instead of multiplying by 100, what we're going to do is we're going to just use that fraction as a conversion factor within our dimensional analysis. All right, so with that said, let's go ahead and look at some examples of how this would work. So our first example here asks us how many grams of pure magnesium could be recovered from the decomposition of 49.4 grams of magnesium fluoride. So I'm going to start this off exactly like we've been starting off our problems thus far. I'm going to look for my how much, what is, how many statement. I notice that we're trying to solve here how many grams of pure magnesium could be recovered from the decomposition of 49.4 grams of magnesium fluoride. And I'm like, ooh, that's a different substance than what I have here. So I'm going to need to show that formula throughout my work. So we need to get ourselves a formula for magnesium fluoride. Formula writing strikes again, y'all. So magnesium is Mg with a +2 charge. Fluoride is fluorine with a -1 charge. By the way, I knew it was ionic because it's a metal and a nonmetal. Those do not balance out, and so to balance them, I would need to write MgF2. All right, so I want to kind of think about, okay, what do I need in order to solve this problem? So I'm going to go consult my heart chart and kind of see where I'm at. I see right now I have grams of a whole entire compound. I'm trying to get to the grams of an element inside of it. So right now, I'm here at mass of a compound, and I'm trying to get to the mass of an element within it. And I'm like, ooh, that means I'm going to be using a mass ratio. Now, every year I get questions about, well, could I try using a particle ratio here? Like, would that work? And it would, but let me kind of talk you through all the steps you would need to do. You would have to go from the mass of the compound to moles of the compound, moles to particles of the compound, in this case formula units, set up a particle ratio to get to atoms, and then take that atoms back to moles and then back to mass. So you can see here that would require 5 steps, whereas if I just use a mass ratio, that would only require 1 step. So I don't know about y'all, but 1 step sounds a lot easier to do than 5 steps. So that's why I'm going to do this with a mass ratio instead of utilizing a particle ratio. So once I know I need a mass ratio here, I want to think about what I need where. I'm only going to need 1 step for a mass ratio. So if grams of magnesium fluoride are here in the numerator on top, that means on this step, I know I'm going to need the grams of MgF2 here on the bottom. I'm trying to get into grams of specifically just magnesium. So in order to set this up for a mass ratio, I need to think about essentially the percent composition setup. What's this total molar mass versus what percent or what portion of that mass came from just the magnesium inside of it? Now, I'm not going to need to actually physically calculate the percentage. Just setting up that fraction is going to be enough that then I can apply that fraction to that original mass that I had. All right, so I'm going to pull out a calculator. I'm going to pull out my periodic table. We're going to get ourselves a molar mass first for the MgF2. So I see that Mg is 24.30. There's only 1 of those in my compound. I have 2 fluorines though. Each fluorine is 19 apiece. So I'm going to do that 19 times 2. And that's going to get me a total molar mass here of 62.30. So now I want to think about, well, what portion of that mass came from specifically just magnesium? Well, if I think about this here, I only had 1 magnesium and it was 24.30. So that's all I would need to put on top. Now, if the fluorine was asked about, for fluorine, keep in mind that there were 2 of those, so that 19 times 2 would have needed to go up here. So we have to be really careful when I'm setting up a mass ratio, because again, if there were multiples of that particular element, when I set up that mass ratio, I want to include that multiple in there, okay? All right, so look what we've done. Magnesium fluoride grams would cancel out. We have grams of magnesium, and that's what I was trying to get to. So that means I'm ready to plug this in and calculate it. So we're going to have our 49.4, open parentheses, 24.30, divided by my 62.30. And again, I want to round this for significant figures. I noticed my given number had 3 sig figs, so I'm going to include 3 significant figures here. So I'm going to report 19.3, and that's going to be grams of magnesium. So let's look at one now that we had more than just 1 of a particular element. So go ahead and flip to the next page. And let's look at our next example here. This next one says, hey, how many grams of oxygen are present in 156.8 grams of calcium phosphate? All right, so I look for how much, what is how many statement. I have how many grams of oxygen. So I'm going to put question mark grams of oxygen here. My starting value is 156.8. And that is grams of our calcium phosphate. And I'm like, oop, I'm going to need a formula for that because it's a different substance than just the oxygen by itself. So I say, okay, well, this is ionic. I have a metal, and I notice the 8 here means I had a polyion. So I know I'm going to need to balance out charge since it's ionic. So I'm going to have calcium, which is positive 2 because that's in group 2. Phosphate is PO4 negative 3. I notice that those do not balance out. The lowest common multiple between 2 and 3 is 6. So to get to positive 6, I would need 3 of the calcium ions. For the phosphate ions, since I need more than one of it, I need to put a parenthesis around it. And I'm going to need 2 of those. All right. So again, if I didn't know what I was doing, I would think, okay, let me go look at my heart chart. Now, this is where people always ask, well, wait, do I get this heart chart like on a quiz or a test or something like that? Well, the answer is no, but you could always draw it out if you wanted to. So keep that in mind. If you like, having something like this, you could always draw this out. I have a lot of students that first thing they do when they get the test on this is they go draw out their heart chart real quick, just so that way they kind of have it that they can use as a reference. Some people can do it without it. That's totally a personal preference on y'all's part. So I see again, I'm trying to go between the mass of an element and the mass of an overall compound. So again, I'm going to be using a mass ratio here to solve this problem. So if I think about where my pieces go, grams of the calcium phosphate were here on top. So I want to put the grams of the calcium phosphate. Ooh, squeezing that too there. Here on the bottom. I'm going to be going to the grams of the oxygen that are inside of it. Now, this molar mass is a little kind of trickier. I'm going to really have to think about it here. So I'm going to get out my calculator. I'm going to get my periodic table ready to go here. All right, so our first element here was calcium. We're going to have 40.08. There's 3 of those. Then we are going to have, for phosphorus, we're going to have 2. Remember that 2 outside of the parentheses distributes to things that are inside of the parentheses, just like math, just like algebra. So our phosphorus is 30.97 here. And so I'm going to take that and multiply that by 2. Our oxygens here is 4 times 2, so that's going to be a grand total of 8 of those. So I'm going to have my 16 for my oxygen times 8. And I get a total molar mass there of 310.18. Now, here's where you got to be careful. We next want to put grams of oxygen here on top. But think about how many oxygens were down here. We had 4 times 2. So out of this 310.18, there were 8 oxygens in there, all contributing to that molar mass. So that means really the 16 times 8 is what should go on top. Now you can either write the 16 times 8 or 8 times 16 up there, however you want to do that, or you can just write the 128 grams. That choice is totally up to you, how you want to illustrate that. I a lot of times will just write 16 times 8 just to remind me that yes, I indeed did account for my subscripts there. So totally a your preference kind of deal. You just want to make sure that you're putting that total mass from the oxygen here out of the 310.18. So now I'm ready to plug all of this in. I have 156.8, open parentheses, 128 over the 310.18. And I see that I get a lot of digits. I want to show here 4 significant figures. So I'm going to show 64.71. So that's 64.71. 0.71, and that's going to be grams of oxygen that are inside of this compound here. Now, I'm going to give you kind of a word of wisdom. If you're ever wanting to double check whether or not your answer logistically makes sense, okay, whether or not you flipped this ratio here. Remember, if this is the mass of the overall compound you should have less mass of oxygen inside of it, right? So you shouldn't come up with a number here that's bigger than 156.8 because you should have less oxygen versus more of the overall compound. So just keep that in mind. Always ask yourself, does my answer logistically make sense here? Okay. All right, let's look at one more that has a little bit of a different quirk to it. This one says, hey, how many grams of potassium carbonate would be present if you know there are 35.0 grams of potassium in the sample? So first off, I'm looking for how many grams of potassium carbonate. Well, potassium is K with a positive 1 charge. Carbonate is CO3 negative 2. I see that those do not balance, so I'm going to do K2CO3. I'm starting with 35.0 grams of potassium in the sample. Now think about how this one's a little bit different. The other ones that we've done already typically had a grams of the whole compound, and we were looking for the grams of the oxygen inside. Here we know the grams of the potassium inside, and we're looking for the mass of the whole compound. So I should be looking for here a number that's bigger than that 35.0 because, again, I'm looking for the mass of the whole thing here. But I can approach this in the same way. So again, if I look at my heart chart, I'm still trying to go between mass of a compound and mass of an element within. So I'm still going to be using a mass ratio, but now what's going to happen is that my units might be flipped around. And so this is where we could potentially have the total molar mass on top and the mass of the element by itself on the bottom. So this is where this could now flip around. So with that said, we know we're going to be doing a mass ratio here. So I'm going to go ahead and put my 1 step, but this time, since grams of potassium were here in the numerator, I'm going to put the grams of potassium here on bottom, and I'm going to be putting the grams of the K2CO3 on the top. So now I'm going to go grab my periodic table and get ourselves some molar masses here. So for the K2CO3, I have 2 Ks at 39.10 apiece. I have carbon, which is 12.01, and then 3 oxygens at 16, and there's 3, and that gets me a total molar mass here of 138.21. But think about this time where that goes. That's going to go with the total molar mass. That's the molar mass of the K2CO3 altogether. So now, when I go to put the grams of potassium, I want to think about, well, there were 2 potassiums inside of that. And each of those potassiums were 39.10 apiece. So that means I'm going to have 2 times the 39.10 down here. So again, you could report it this way, or you could just write the 78.20 down there. That choice is up to you. Whatever's going to help you remember to make sure that you've addressed that subscript, the fact that there's 2 of those potassiums inside of there. All right, so now I'm ready to plug this into my calculator. So I'm going to have 35.0, open parentheses, 138.21, over, and then here if you're doing this, just kind of be careful with how you're plugging it in for order of operations purposes. I'm going to put that 2 times 39.10 in its own little parentheses. That's why sometimes it's helpful to go ahead and multiply it. You don't have to worry about order of operations there. And then I'm going to close off the whole parentheses altogether. And I see that that comes out, and I want to use 3 sig figs, so right around 61.9. And that is going to be grams of the K2CO3, which again, asking ourselves if our answer makes sense. I should have more of the overall compound versus less of the element inside of it. And in fact, that is the case. So that means we must have done something right. So anyways, I hope you're feeling good with these. Again, it's really important to be practicing with these calculations. The more you practice with them, the more you're going to get confident with them. It's also important to be able to recognize what kind of problem you have when. And so in your homework, you're going to see quite a bit of mixed practice where it's a combination of problems. And so you're having to think about, well, hey, is this a particles within problem? Is this a percent composition problem? Is this a mass ratio problem? What kind of example do I have here? And so you're going to have to process through that and think about how to solve it. Anyway, I hope you're feeling okay. If you have any questions or need any help, please feel free to email me. Bye, guys.